Ameliorating of residential building energy performance by using nanotechnology. Al-Ras Housing, a case study. Abstract. Recent years have witnessed progress in equipping residential buildings using different methods, building materials, and types, some of them compatible with the surrounding environment, and many of them are not suitable, which leads to high rates of energy consumption within them. This confirms the necessity to search for new ways to rationalize energy consumption, especially in residential buildings. With the rapid technological development, there are now many advanced architectural treatments that increase the interior quality of life, and greatly contribute to rationalizing energy consumption. Therefore, this study came to contribute to raising the internal environmental efficiency of Saudi housing, which lacks many modern applications that can be used, due to its suitability to the difficult nature of Saudi housing. Nanotechnology was used in the finishing of residential buildings in the study area, due to its various properties that enable it to resist difficult environmental factors, and an advanced program was used to measure the environmental efficiency of buildings before and after the use of the most effective architectural elements and finishes. Then come up with a set of findings and recommendations that must be considered in the future. Keywords: residential buildings, nanotechnology, energy consumptio, thermal comfort. Introduction. In recent years, many unexpected climate changes have occurred in the world in general, and in the cities of Saudi Arabia in particular, and this has led to an increase in energy consumption rates, especially in residential buildings, which were not sufficiently equipped to face these changes. As the per capita consumption of electricity increased from 7019 kW/h in 2007 to 9137 kW/h in 2014. In order to rationalize energy consumption, the kingdom established the Saudi Energy Efficiency Center, which has undertaken many initiatives in this field, perhaps with the aim of creating and raising the level of community awareness of the importance of rationalizing energy consumption through a set of correct environmental behaviors that in the future lead to reducing consumption too. That is why the kingdom's Vision 2030 came to work to improve the quality of life for its residents and to develop plans and strategies that achieve this goal. Where the advanced infrastructure has been established, in addition to developing future plans to complete the requirements and needs that create an integrated environment for its citizens that includes basic services of high quality, we raise the level of quality of life for everyone. 3. Previous studies. A group of previous studies conducted in 2014 with the aim of knowing the percentage of experience of workers in the construction sector and related to knowledge of new design solutions related to energy efficiency and rationalization within residential buildings, where the results indicated that only 31% of the respondents in the questionnaire have only knowledge without practice, while only 12% have the experience and practice. The study also indicated that real estate developers, contractors, and investors are among the least familiar with these solutions. 4. A second study in which researchers used simulation software, DO, on an apartment building in Dammam, and it resulted in the possibility of reducing energy consumption in buildings if the design and operation were done using passive design strategies. The study confirmed that the building's external envelope, including building materials, the size of the windows, or the type of glass used, in addition to the behaviors used in the operation of the building, have a pivotal and important role to reduce energy consumption, which amounts to 38% of the total energy consumed annually. 5. Methodology. Based on the results of the second research study, the research will follow the same analytical approach, by studying an existing residential building affiliated with a new residential neighborhood in a city in the Kingdom of Saudi Arabia, and using one of the advanced measurement programs, hourly analysis program, HAP, to know the thermal behavior of the building in the current situation, and then changing the materials of its outer surface, external walls, outer ceiling, glass, with alternative materials of nanotechnology, then measuring again and knowing the new thermal behavior of the building, then measuring the amount of thermal decline of the building, and comparing the results. Energy consumption in the kingdom's residential buildings. In 1995, 43,733 building permits were issued, and this number increased greatly to reach in 2005 to 113,519 permits, and this is based on the report submitted by the Ministry of Municipal and Rural Affairs for building permits in the construction sector in the kingdom. 6. On the other hand, a scientific study confirmed that the kingdom needs to build more than 2.32 million residential buildings until 2027. Most of the buildings that were built have met the residents' living requirements, without considering the environmental standards, which resulted in buildings with low thermal performance, and therefore energy-consuming mechanical solutions were relied upon to provide an appropriate environment and thermal comfort inside the buildings. On the other hand, we find that the housing sector in the kingdom consumes 44.9% of the total energy sales of the Saudi Electricity Company, while the government sector consumes 15.1%, the commercial sector 16.1%, and the industrial sector 17.6%, according to the statistical report. The Annual Statistical Manual of the Saudi Electricity Regulatory Authority, which was issued in 2018. Moreover, these residential buildings contributed to increasing the emission rates of carbon dioxide, because the air conditioning units used in them with a capacity, 2 tons, resulting in emissions of carbon dioxide gas at a volume of 2 kg/hr. 9. 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38 tone. Fig. 1. Carbon dioxide emissions in the Kingdom Arabia, K.S.A, compared to some countries, in tons, in 2018. Nanomaterials. Nanotechnology was able to open new horizons to the world in the field of building and construction, by providing many building materials with improved qualities and functions, which contributed to rationalizing energy consumption, and this technology now seeks to reach low-cost building materials that increase the lifespan of the building, and reduce of his need for maintenance work. No isolation. Today, nanoscale insulation materials are used to raise the energy efficiency of buildings and reduce the rate of pollutant emissions, as the efficiency of these materials is 30% higher than traditional insulation materials. These materials can be used in a variety of forms, including solid panels, thin films, and insulating coatings. 10. The research will address thermal insulation only as it is considered the most appropriate for the project under study. Thermal nano-isolation. The Saudi Ministry of Electricity issued a statement last year, in which it stated that the consumption of air conditioners alone in the summer reaches 70% of the total electrical energy consumption at the level of the Kingdom Electricity Company, 2019. Here comes the role of thermal insulation materials as one of the most important materials that must be used to rationalize energy consumption. There are several types of nano composition, the most important of which are vacuum insulation panels, VIPs. These panels are characterized by large thermal insulation, with a thin thickness of 8 to 35 mm, and the coefficient of thermal conductivity of them reaches 0,0035 W/m2K at 25 degrees. It is less than 5 to 10 times of material's traditional insulation, and its lifespan ranges from 30 to 50 years, and it also does not require regular maintenance. 11. Aerogel. It is a low-density gel in which the liquid is replaced by gas. It consists of 5% solids and the rest gaseous substances. It is characterized by low weight, 60-80 kg/m3, high thermal insulation capacity, 0,28 W/m2K, with transmittance to natural lighting, up to 75%. It can carry even 2,000 times heavier than its weight. 12. Thin film insulation. It is used for thermal insulation of window glass, and it consists of a thin layer of nano steel fibers resistant to rust, which reduces the rate of passage of sunlight, as it blocks 97% of infrared radiation, 99% of the permissible temperature of the inner spaces, 2 to 3 degrees C, compared to traditional insulation material. 13. Al Ras Housing Project. Case study. The Al Ras Housing Project is located in Al Ras Governorate of the Al Qasim region from the eastern side, and is about 85 kilometers from the city center of Buraydah. It is one of the housing projects of the Ministry of Housing, which was completed in July 2020, and the project contains 94 identical housing units on an area of 245,000 square meters. It is now available for sale. 14. Knowing the specifications and standards of Saudi construction, and the extent of its compliance with the Saudi Building Code. The site of the project, which prevails in hot summer weather, Al Ras Governorate, Al Qasim region. One of the development projects of the Housing Ministry. Housing projects needs for more energy conservation. The large number of housing projects in the kingdom, similar to this one. Climate for the case study. The climate of Al Ras Governorate in Al Qasim, very hot desert, especially in summer, and very cold in winter, so the general climate is described as arid, and it is characterized by irregular rains throughout the year, especially in the summer, and the Qasim region is generally known by the frequent seasonal dust storms. 15. Climatic data for the study site. The climate consultant program was used to know the temperatures, wind speed, and humidity, and the thermal comfort scheme inside the spaces for different periods of time, and to study the best methods and strategies proposed by the program to achieve thermal comfort standards for the buildings of the area under study. Fig. 5. The minimum and maximum temperature for the study area. We note that, the average temperature rises for the months of July and August, 39 degrees C, which is high compared to December and January, 14 degrees C. As for humidity, its highest rates are in November and December, 56%, and the lowest in the month July, 19%, only, which is an indication of severe drought, with which it is necessary to find suitable solutions to increase the humidity rate for this period, and the wind speeds in the region in general are close, reaching a maximum, 3 m/sec, second and a minimum of, 2 m/sec. Climatic data for the study site. Fig. 6. The difference between the maximum and minimum temperatures for the study area. The graph shows that the highest temperature for the observation point is in July, reaching more than 45 degrees C. And the lowest temperature in the months of January and December, 0 degrees C. This large discrepancy between daily degrees requires the choice of design strategies such as high thermal insulation efficiency for walls and ceilings, and it is noted that the thermal comfort zone is located between 20 to 70 degrees C throughout the year. Fig. 7. The intensity of solar radiation for the study area. Fig. 8. Humidity levels for the study area. Simulation software used to calculate thermal loads. To calculate the thermal loads of the housing unit under study, the hourly analysis program, which is known as HAP, of the International Carrier Company, will be used. The building material used for the building exterior. Fig. 9. Hourly analysis program, HAP, of the North American Commercial Corporation of Carrier. Ameliorating the building energy performance. It is need to be assessed the following characteristics. Heat transfer coefficient, U, W/M2K. Heat transfer coefficient, thermal transmittance, is the sum of the resistors, RC, for each building material and the external surface resistors, RSO, and the envelope interfaces. The R value, M2K/W. This is the material thermal resistance, and calculated from relation, R equals T/M2K/W, T, material thickness in meter, the thermal conductivity of material. Current status of housing unit. Heat transfer coefficient will be calculated for each component separately by detailing the building materials used for the residential unit in its current state, and then improving some properties of the building materials used using nanotechnology, and then calculating the thermal transmittance again as follows. External walls. The external walls of the residential units consists of several layers and their arrangement from inside to outside as following. Plaster layer with thickness 1.5 cm. Cement layer with thickness 2 cm. Concrete block with thickness 20 cm. Cement layer with thickness 2 cm. Plaster layer with thickness 1.5 cm. Fig. 10. Heat transfer coefficient of external walls layers in the current situation. By entering this data into the program, it will calculate the heat transfer coefficient of each layer separately, and the final average of the surface layers, which equal 0.892 W/M2K. External ceiling, the roof. The ceiling of the residential units consists of several layers and their arrangement from bottom to up as following. Gypsum layer with thickness 2 cm. Reinforced concrete layer with thickness 15 cm. Heat insulating layer with thickness 5 cm. Sand layer with thickness 6 cm. Regular concrete layer with thickness 20 cm. Ceramic tiles layer with thickness 2 cm. Fig. 11. The heat transfer coefficient of the ceiling layers in the current situation. The program calculated the heat transfer coefficient of each layer separately, and the final average of the surface layers, which equal 0.207 W/M2K. External windows. In the current situation of the residential unit, double glazed windows, 3 mm, and an air layer between them, 6 mm, were used, and the overall shade coefficient, 0.717. The value of the thermal transfer coefficient for it was 3237 W/M2K. Fig. 12. Heat transfer coefficient of the external windows in the current situation. The proposed status of housing unit. In the proposed status of the building, the insulation material used in the outer shell was changed, and the glass used in the windows was changed to materials developed using nanotechnology techniques, namely vacuum insulation panels, VIPs, is used in walls and ceilings. Aerogel was used in windows. This is because of their advantages in reducing thermal loads and improving the quality of the internal environment of the building. External walls. In the proposed status for the residential unit, it was proposed to insulate the external walls by adding vacuum insulation panels, or what is known as vacuum insulation panels, VIPs, which are characterized by a low thermal conductivity of 0.005 W/m2K, 16 as shown in figure 13. The new external walls layers and their arrangement from inside to outside as following. Plaster layer with thickness 1.5 cm. Cement layer with thickness 2 cm. Concrete block with thickness 15 cm. Vacuum insulation panels, VIP, with thickness 3 cm. Concrete block with thickness 10 cm. Cement layer with thickness 2 cm. Plaster layer with thickness 2 cm. Absorptivity 0.675, and outside surface color is medium. Fig 13. Heat transfer coefficient of external walls layers in the proposed status. The total thermal transfer coefficient for the walls in the proposed status is 0.120 W/m2K. External ceiling, the roof. In the proposed status, it was proposed to remove the current insulation of external ceiling and use vacuum insulation panels, or what is known as vacuum insulation panels, VIPs, which are characterized by a low thermal conductivity of 0.005 W/m2K, 16 as shown in figure 14. The new external ceiling layers and their arrangement from bottom to up as following. Gypsum layer with thickness 2 cm. Reinforced concrete layer with thickness 15 cm. Vacuum insulation panels, VIP, with thickness 3 cm. Sand layer with thickness 6 cm. Regular concrete layer with thickness 20 cm. Ceramic tiles layer with thickness 2 cm. To achieve the best possible results, both will be assumed. Absorptivity 0.900, and outside surface color is dark rather than the medium color. Bedroom -1 kitchen. Stair and washer living room. Dining room guests room. Fig 14. Heat transfer coefficient of the external windows in the proposed situation. The total thermal transfer coefficient for the external ceiling in the proposed status is 0.107 W/m2K. External windows. In the proposed status for the residential unit, windows of one of the applications of nanostructures, which are characterized by low thermal permeability, are used, which are called aerogel, one of the products of the aerogel, and the overall shade coefficient, 0.811. The thermal transfer coefficient is 0,600 W/m2K, at a thickness of 30 mm, 17. Fig 15. Heat transfer coefficient of external ceiling layers in the proposed status. Thermal transfer coefficient / thermal transmittance, U value. Biding spaces. To calculate thermal transfer coefficient, U value, for the building and to know the difference before and after the improvement, the building must be divided into several spaces, and calculating both. The monitoring point. After the spaces were divided, their area and window areas were calculated and each space was directed separately, as shown in the following tables, and the locations of the voids were clarified for the unit and its direction. Safety factor, 10%. The monitoring point listed in the HAP program is King Abdulaziz Airport in Qasim. Fig 17. Details of the monitoring point for King Abdulaziz Airport in Al Qasim region included in the HAP program. Thermal transfer coefficient in current status. The thermal transfer coefficients of the building are calculated for each space, and the envelope materials used in the outer envelope of walls, ceilings, and windows are calculated in their current state, which was previously detailed. Thermal transfer coefficient in proper use status. The thermal transfer coefficients of the building were calculated for each space, but only at the stage the outer shell material was changed from walls, ceilings, and windows to nanotechnology materials, where vacuum insulation material, VIPs, are used in walls and ceilings. Aerogel was used in windows. By comparing the housing unit in its current state and after changing the materials used with nanomaterials with the highest energy efficiency, then measuring it using the HAP simulation program, where the measurement was made at the highest time of the year, and by fixing both the study area and the safety factor, 10% found that the thermal transfer coefficients of the housing unit in the current situation, 22.8 W/m2K. The thermal transfer coefficients of the housing unit in the proposed situation, 15.9 W/m2K. The thermal transfer coefficients decrease by 6.9 W/m2K. Conclusion. The project under study belongs to the Saudi Ministry of Housing, and it is one of the projects that require high energy efficiency. This project is very similar to many of the current Saudi housing projects, and therefore the results of the study can be used in developing existing housing projects in general, and specifically planned to be implemented in the future. Internal residential spaces are directly affected by the external climate, which is transmitted from outside to inside through the outer envelope that includes walls, ceilings, and openings, external. Each of these three elements has a direct effect on the thermal transfer between the internal and external climate, and therefore the cover of the residential building under study was studied before and after the use of nanomaterials, and the study showed the effectiveness of these new materials in reducing the building's external heat acquisition rates by 6.9 W/m2K. In addition to taking into account both orientation, shape, and shading of the building. From the above, we find that nanotechnology for architecture has succeeded in achieving many solutions to raise the efficiency of the materials used, extend their lifespan, and thus raise the energy efficiency of the building and increase its resistance to surrounding environmental factors, as well as contribute to preserving the surrounding environment by reducing carbon dioxide emissions, as well as reducing the depletion of non-renewable natural resources. Acknowledgement. Authors grateful to the Department of Architecture at the College of Architecture and Planning in Qasim University for the encouragement and support. Authors and affiliation. Sherif El Said El Said, graduated from Faculty of Engineering, and Shams University, Egypt in 2004, then obtained a master's degree from Cairo University in 2007 and PhD degree in 2014. Now, he working as an assistant professor in Department of Architecture, College of Architecture and Planning, Qasim University, Kingdom of Saudi Arabia. Almondir Salih Al-Suhaibani. Graduated from Faculty of Architecture and Planning, Qasim University, Qasim, in 2015. Now, he prepare a master thesis in architecture in College of Architecture and Planning, Qasim University, and working as senior architect in Saudi Arabian Parsons Ltd, Kingdom of Saudi Arabia.